Hi everyone. Thanks to the organizers for giving me this opportunity to present my work here. So, my talk will be based on these two papers. One was written with Teppei Okumura and the other one is single author. Both of them were published in the Astrophysical Journal Letters. So this work is on cosmology in an extended parameter space which has basically 12 parameters. Now, DESI showed preference for dynamical dark energy at the level of currently it's 2.8 to 4.2 sigma, depending on the supernovae data set used. But even without that, DESI plus CMB alone shows a 3.1 sigma preference for dynamical dark energy in the CPL parameterization. So in DESI DR2 paper, the data release 2 paper, they see a phantom crossing happening for a multitude of parameterizations for dynamical dark energy using 2 parameters. Now, this uses total 8 parameters basically. 6 parameters for lambda CDM and then 2 for dynamical dark energy. Now, DESI also has a very strong constraint on the sum of neutrino masses in lambda CDM, which prompted people to talk about negative neutrino masses or maybe neutrino decay, which is masking the effect of neutrino masses. Because if you extend this posterior, it will actually peak in the negative neutrino mass. So, and it's also even challenging the normal hierarchy, which requires 0.06 eV of minimum neutrino masses. So the bounds do relax with dynamical dark energy, but still we do not see a peak in the posterior in the positive neutrino mass direction. So in our paper, what we did is we used a 12 parameter model. So we have the first 6 lambda CDM parameters, then W0 WA for dynamical dark energy, then simple extensions, an effective or effective number of neutrino species, sum of neutrino masses, then running of the scalar spectral index, and A-lens, which is a artificial scaling of the lensing amplitude. These are simple extensions, and so the power spectrum basically has AS, NS, and this extra alpha S parameter, which is the scaling of the spectral index basically. And we also use CPL for dynamical dark energy. Now, our main goals are to check for the preference of dynamical dark energy in this extended parameter space, if it survives or not. We want to provide a reasonable bound on the sum of neutrino masses by, we want to provide a robust bound because the parameters we choose like W0, WA, and A-lens, they are correlated with sum of neutrino masses, and that will change the bound, and we want to see if we can see some evidence for positive neutrino masses. We want to give a definitive answer to the lensing anomaly case, which was there with the Planck PR3 likelihoods, but it's not present in the Planck PR4 likelihoods, but in lambda CDM model. Nobody has checked it for dynamical dark energy. Now, lensing anomaly is a case that where the data prefers more lensing than that is theoretically expected. So the A-lens value should be equal to 1, and if it deviates by more than 2 sigma from 1, then we have a lensing anomaly. We also want to assess the level of the Hubble discrepancy in our 12 parameter extended cosmological model. So how far we can decrease the tension from currently the tension is at 5 sigma, so we want to see how much we can decrease it. So we use Planck public release 4 likelihoods for high L temperature and polarization along with low L polarization data. And we use the commander likelihood for Planck 2018 low L temperature data. For lensing, we again use the latest Planck PR4 and Atacama Cosmology Telescope data release 6 lensing likelihoods. For BAO, in the first paper, we had data release 1 of DESI, and in the second paper, we have data release 2 of DESI. For supernovae, we use Pantheon Plus and DES year 5 separately. And these two have some supernovae which are common, so you can't use both of them together. So you can't use Pantheon Plus and DES year 5 together because then there will be some double counting issues. For weak lensing data, we use dark energy survey year 1 data. So one of our main results is that when you go to a 12 parameter space, then with Pantheon Plus along with CMB plus BAO, there's red contours, 1 sigma and 2 sigma red contours. What we see is that the cosmological constant is at the edge of the 2 sigma range, and for DES year 5 it is excluded at more than 2 sigma. So the evidence for dynamical dark energy in this 12 parameter model is basically inconclusive and data set dependent. And with Pantheon Plus, we still have a part of, so this parameter space is for quintessence, and quintessence where the equation of state doesn't go below -1. So some parameter space is still allowed with Pantheon Plus, but not with the SER 5 basically. So this is a relatively important result because DESI's claim is much stronger, but simple extensions to their model can actually reduce the tension to a large extent and allow cosmological constant at least at the boundary of 2 sigma contours. For neutrino masses, when we use only CMB plus BAO plus supernovae, what we see is that CMB plus BAO gives us a peak in the positive mass range, and same with CMB plus BAO plus DES 5, but Pantheon Plus doesn't give a peak basically in the positive mass range. But after we use the weak lensing data, there is a strong correlation with S8 and some of neutrino masses, and that makes the peaks much better. And we actually have the first 2 sigma detection of some of neutrino masses of around 0.19 plus 0.15 minus 0.1 EV with this CMB plus BO plus DES year 5 plus the DES year 1 weak lensing data. So this detection is at 2.1 sigma level, and with Pantheon Plus we get a detection of at the level of 1.9 sigma. So yeah, this is quite a big result in this paper. For lensing anomaly, we have some interesting result that so with CMB plus BO plus supernova, it is okay with A lens equal to 1 at less than 2 sigma. So but when we use weak lensing data, the smaller S8 values of weak lensing make the lensing anomaly much worse, and it's actually a more than 2 sigma tension when we have the weak lensing data. So these plots basically. So as you can see, the supernovae data have produced similar values of A lens, but when we use weak lensing, the result changes. So yeah, okay. So this is again for the first time we show that the existence of the lensing we show the existence of lensing anomaly can depend on non-CMB data sets. So previously this lensing anomaly was associated with Planck 2018 likelihoods or Planck PR3 likelihoods, and Planck PR4 likelihoods did not show any existence of lensing anomaly in the lambda CDM model, but in a dynamical dark energy model you can find the evidence of lensing anomaly with weak lensing data. In case of Hubble tension, in the first paper we found that the tension persists around 3.2 to 3.9 sigma with CMB plus BO plus supernovae. In the plots you can see that these are Planck plus lensing, and they don't, so Planck, CMB is not sensitive to H0 that much because H0 is very much correlated with these W0, WA parameters, and with addition of BAO you get some constraints, and for proper constraints you do need the supernovae data because when you constrain W0, WA with supernovae, then only you can get a proper constraint on H0, and then Hubble tension persists at the level of 3.2 to 3.9 sigma in the DESI DR1 case, but in the DR2 case, we find it's a bit larger at 3.6 to 4.2 sigma, depending on the supernova dataset used. So you can say that the Hubble tension is quite robust, and you need actually much more non-trivial extensions to lambda CDM to solve Hubble tension. These simple extensions are not enough. For the S8 tension, we find that with DES year 3 weak lensing data, it is reduced to 1.4 sigma with CMB plus BAO plus supernovae. So the main effect seems to be coming from Planck PR4 likelihoods instead of Planck PR3, because with Planck PR3, the tension was more than 2 sigma. So S8 tension is not to be considered a strong tension anymore in cosmology, basically. With the new kids results, that has become even more apparent that the S8 tension is not a big tension anymore. So these are a few degeneracies of sum of neutrino masses which are important. Out of them, these three, with WA, ALNs, and S8, these are very important because weak lensing data prefers slightly lower values of S8, and that chooses slightly higher values of sum of neutrino masses. At the same time, it also chooses slightly higher values of ALNs as well. So overall, you can see from these correlation plots that how the results come about, basically, especially the detection of neutrino masses because of the S8, small S8 tension, which is not a big tension anymore. That is why we can combine the data sets together, basically. So to summarize, CMB plus BO plus Pantheon plus allows for a cosmological constant at the edge of the 95% contour. So the evidence for dynamical dark energy component is dataset dependent and not conclusive yet. We find the first 2 sigma detection of non-zero positive neutrino mass sum, and the peaks in the sum of neutrino posteriors indicate that in future we might find a 5 sigma detection as well. We recommend this bound for the particle physics and cosmology communities to use as reference. For lensing anomaly, we find that even with Planck VR4 likelihoods, we find the existence of lensing anomaly could depend on non-CMB data sets, and simple extensions to lambda CDM explored in this study are not enough to solve the Hubble tension. And lastly, the S8 tension with DES 3 is reduced to 1.4 sigma. Yeah, thank you.
Two questions. One is something that you already touched on. You are, in principle, combining data sets that are maybe in tension. Let's say CMB and DESI. You are combining them in the model rather than checking if the extended model with just CMB allows you the DESI parameter space. Why is that? And second, I'll ask the question, you can answer. The neutrino mass being negative in DESI alone is simply a measurement of omega matter at late times being slightly lower than what CMB prefers. Do you understand why it shifts in your analysis? Is it AS absorbing most of it, or is it S8 absorbing most of it?
Okay, so to answer the first question, in the CPL parametrization, that omega m tension doesn't actually occur, that occurs in the lambda CDM model. So in lambda CDM, BAO prefers lower omega m, and the tension is at the level of 2 sigma as far as I understand with CMB data. But when you allow for W0WA, then this omega m tension goes away. It's much less than 2 sigma, so it's not an issue to analyze CMB plus BAO together. Also, supernovae data actually prefers slightly higher omega m. So if you just combine Planck with supernovae data, you will get even a 3 sigma detection if you don't take BAO data at all. In lambda CDM model, you don't have to consider even dynamical dark energy. So it's important to note that the detection happens with BAO data, which is a new thing because people haven't seen it before. Now the second thing is that, as I said, there is a large negative correlation between S8 and sum of neutrino masses, and as it happens, weak lensing actually prefers lowers S8, but the tension is at the level of 1 sigma with DES year 1 weak lensing data. And if you consider this 12 parameter model, then calculate S8 from CMB plus BO plus supernovae, and then calculate S8 from weak lensing data, the tension is at the level of 1 sigma. So there is no problem combining them together. So in that sense, this is a detection where we have used data sets which are compatible with each other in this particular model. Of course, in lambda CDM, there might be problems, but not in this model at least.
About the A lens parameter, which characterizes the strength of lensing just based on 2-point correlation. The ACT and SPT data over the years have shown that A lens is consistent with 1.
Yeah.
So have you considered looking at it?
I have not used ACT or SPT data. What we have used is the Planck PR4 likelihoods, which also don't show any A lens anomaly in the in lambda CDM basically. So in this case, we see an A lens tension above 2 sigma with the weak lensing data, but not without the weak lensing data. So it's again happening because of this correlation. So S8 and sum of neutrino masses is correlated, and A lens and sum of neutrino masses are also strongly correlated. So lower values of S8 chooses higher values of sum of neutrino masses as well as higher values of A lens basically.
Thank you.
Hi, yeah, just a quick question on the similar lines. So one of them is already taken regarding A lens, that when you combine ACT and SPT, when you combine ACT and SPT, A lens is consistent with 1.
Yeah, only with in lambda CDM usually.
No. So the A lens, the problem is usually coming from the CMB TT with only a few multiples localized around 1400 values of L.
Okay.
Multiples, but my main question still remains is that when you're talking about kids' data set, the photo-Z errors in the bins of the lensing, there is a uncertainty in the measurement of the redshifts of those window functions. And that's a possible way where the sigma 8, S8 tension may be already coming from. So how do you understand the possible systematics in different data set is not driving your neutrino mass to a positive value?
Here we are not using kids for that instance. We are using dark energy server.
Kids have shown this, that they have a problem. DS have not shown this. That's one of the things we compare with. But kids have shown that depending upon the photo-Z bins, that window function, your SI changes. But I want to understand that how do you know that this is not sourcing you a systematic error? So the main problem is the amount of clustering seen in BO measurements and DS is different from what is seen in Planck or what Planck can say.
Okay, so here we are combining CMB plus BO plus supernovae first, and then checking it with weak lensing data. So weak lensing has slightly lower S8, but the two measurements are compatible with each other at the level of 1 sigma. So there might be systematics in DES, and as I said, the lower S8 values are driving the detection of sum of neutrino masses here. So if there are systematic issues that they have to deal with, because I take them as on face value basically. Yeah.
Okay, so let's thank Shobik again.